talked about red blood cells. But there are two other types of formed elements in your blood. The white blood cells are leukocytes. In general, they're there to protect your body. They're part of your immune system. They are there to help you fight off infections, to keep you from being invaded by all the little microorganisms that you will learn about should you choose to take micro with me in the summer. And then the platelets or the thrombocytes. Oh, by the way, red blood cell, one type of white blood cell, little bitty platelet. All right. Now, remember that you got your pluripotent stem cell, the mother of all blood cells. Pluripotent, many potential, much potential, many options. And that, of course, can divide into the myeloid stem cell or the lymphoid stem cell. And then the myeloid stem cell produces 4 of the 5 types of white blood cells, and the megakaryocyte, which is where the platelets come from. Now, back in the day, before they had electron microscopes, they discovered that there were 5 different types of white blood cells. They'd take a blood smear, and they'd take a drop of blood, smear it out, stain it, look at it with a microscope. And what they decided was that there were 3 of the types that they could actually see little granules in the cytoplasm. And there were 2 of the types that they didn't see granules. Well, once they had electron microscopes, what they realized was all 5 types of white blood cells have granules in the cytoplasm. It's just the lymphocytes and the monocytes were too tiny to see with the light microscope. But we still kind of use these old terms, the granular leukocytes, Eos, Basos, and Neutrophils, and the agranular leukocytes, lymphocytes and monocytes. But I wish they'd get away from that because it's really a misnomer now. You probably learned in lab, never let monkeys eat bananas. Yeah. The most numerous type of white blood cell is the neutrophil. Neutrophils are kind of like snowflakes. And one neutrophil doesn't look like any other neutrophil. But what they have is this, it looks like it's got like 4 nuclei in this cell. It's one nucleus, but it's like if you took the round nucleus, if you took like a round thing of Play-Doh and you squished it down into a tube or a cylinder, and then you pinched off parts of it and left little bitty pieces of it attached, that's essentially what happens to the nuclei of the neutrophils. They get squeezed and squished into these little lobes. Instead of it being round, normally if I draw a cell, here's the cell membrane, there's the nucleus, right? Okay. Their nucleus gets squished. And so that you've got little balls, little lobes of the nucleus that are attached with real thin pieces. And for this reason, sometimes they call them PMNs, or polymorphonuclear, many-shaped nucleus, or many different appearing nuclei. And normally, if everything's going on along okay, you're nice and healthy, you have around 65 to 80% of your white blood cells are going to be neutrophils. Now, you don't have to know those numbers. I'm just kind of giving you an idea of what you would see. So when you look at a blood smear, most of the white blood cells you're going to see are going to be neutrophils. The eosinophils and the basophils are a little bit different. You can't, sometimes in the neutrophils, unless you look real close, they don't show up on this photomicrograph, but they're tiny, tiny little, almost like little purple or lilac grains of sand. Those are the granules. Now, interestingly enough, when these neutrophils get activated, for instance, if you've got an active bacterial infection, those granules get bigger, and they almost look like they're angry neutrophils. And they are, because they're starting to produce a lot of the enzymes that help destroy good bacteria. And so, but, sometimes it's hard to see. No bad bacteria. If you've got bacteria, any bacteria in the blood is a bad bacteria. The eosinophils and the basophils have large, big purple, almost like little purple marbles in the cytoplasm. The eosinophils have these orangish red marbles. Another characteristic is the basophil usually has a 2-lobe nucleus. Eosinophil normally has a 3-lobe. Sometimes you'll see a 2-lobe or 3-lobe nucleus. So the nuclei of the eosinophils and the basophils aren't quite as squeezed into as many lobes as the neutrophils. Basophils Usually less than 1%. So if you looked at 100 white blood cells, you might not even see a basophil. Eosinophils, 4 to 8%, something like that. So you might see a few. And again, depending on what textbook you read, you might, these aren't exact numbers, but that's kind of a ballpark. All right, lymphocytes and monocytes are the, quote, agranular. Lymphocytes are going to be somewhere around 25%, 25 to 40 maybe, depending on. And monocytes are going to be around 10%. 8 to 10%. So when you look at a blood smear, these are the cells you see more often. Lots and lots of neutrophils. Every once in a while you'll see a lymphocyte. Might see a couple of those. Might see one of those. Probably have to go look a while to find one of these. All right, lymphocytes are kind of cool. Lymphocytes are just slightly larger than the red cells. And in a lymphocyte, the nucleus takes up most of the room of the cell. So when you look at a lymphocyte, when you're looking at it on a slide, you're looking at it, of course, in 2 dimensions. Remember, it's actually a sphere, but you're just looking at it in 2 dimensions, and so it looks like there's just a little bit of rim of cytoplasm around the nucleus. Monocytes, on the other hand, are the biggest white blood cell. And their nucleus is kind of folded over. Sometimes it looks like a kidney bean shaped. Kind of look like that. But what it is, it's actually folded over like a horseshoe. So if you're looking at a horseshoe from the side, from an angle, it might look like it's a kidney bean shape. It's folded over in half. Sometimes people describe it as butt cheeks. The other thing about monocyte is the cytoplasm tends to be, and again, it doesn't really show up well in these pictures, but if you're looking at a slide, the cytoplasm of the monocyte tends to be more of a gray color. Cytoplasm of a lymphocyte tends to be more bluish. Now, monocytes, remember that all these cells, all 5 types of white blood cells, are produced in the bone marrow. They leave the bone marrow, go into the bloodstream. But monocytes don't stay there very long. Monocytes only maybe spend a day or so in the bloodstream, and then they leave the bloodstream and they go into the tissues. And once a monocyte has gone into the tissue, it's called a macrophage. If it's inside your blood vessel, it's a monocyte. If it's outside the blood vessel, it's a macrophage. Macrophage literally means big eater. Some of these macrophages just wander around throughout your body. You've got macrophages crawling around through your tissues right now. We call them wandering macrophages. They're like nomads. But some of them find an organ that they say, ooh, I like it here. This is a good neighborhood, it's a good school system, a good place to raise children. And so we call those fixed macrophages. Examples of fixed macrophages would be the alveolar macrophages. There are macrophages right now crawling around inside your lungs. In case you get any bacteria or viruses that aren't caught by the nose hairs and the mucus and all that kind of stuff that they get down in your lungs, those macrophages are there to eat those bacteria. You have something called Kupffer cells. It's 1P2S. Those are macrophages that hang out in the liver. Either 2 P's and 1 F or 2 F's and 1 P. You have, when y'all did skin and AMP1, remember these guys? Langerhans cells?
So all of these 3 are the same, but they're just maybe they're in a different location.
They're in a different location. Yeah.
They don't have any other differences.
Oh, they would actually look different. The Langerhans cells usually have these really long cytoplasmic extensions, really long thin pseudopodies.
So So where do they change? I mean, they all start out the same.
They all start out the same, and once they get into the little microenvironment inside each organ,
Okay, that's
the chemicals there
They
can
adapt to their surrounding, kind of what they need to do there.
yeah. Basically, Langerhans cells are crawling along in your dermis, looking for bacteria that have penetrated the skin. Isn't that gross? You've got splenic macrophages, you've got, oh gosh, you got them everywhere, basically, except for the, well, you even got them in the central nervous system. We just call them remember that? Oh, yeah. Yeah. Microplate. In case any bacteria managed to get into the CNS. Now, we said that the white blood cells were responsible for your immune system, fighting off infections. Four of the types, Eos, Basophils, Neutrophils, and Monocytes, are responsible for what's called non-specific immunity. And unfortunately, I don't have a lot of time today to talk about the immune system. Non-specific defense or non-specific immunity refers to the fact that it doesn't matter what type of bacteria, what type of virus, what type of fungus, these cells, monocytes, eos, basos, and neutrophils, always attack the invading organism with the same set of weapons. They do not adapt to the organism that's invading your body. Neutrophils and monocytes eat stuff. They are the cells that are best at phagocytosis. They are phagocytes. It doesn't matter what it is. If they don't think it's supposed to be there, they're going to eat it and try to kill it. Lymphocytes, however, your lymphocytes are, when we think about immunity, what we're really thinking about are the lymphocytes. Lymphocytes are responsible for our, what we call the specific immunity, or sometimes it's called the adaptive immunity. When you are given a vaccination, the cells that are stimulated by that vaccine are the lymphocytes. And so if you're given the hepatitis B vaccine series, there are one or two lymphocytes that can recognize the hepatitis B antigen, the little pieces of the virus that's in that shot. And they will begin to work together to produce anti-hepatitis B antibodies. So the lymphocytes are specific for specific organisms. So lymphocytes are specific, everything else is non-specific. They just attack anything. So, neutrophils. If bacteria get into your body, neutrophils are like, whoo, party. They're going to show up. They are the first white blood cell that responds to bacterial infections. Now remember, you can be infected with bacteria, viruses, parasites, all kind of stuff, fungi, but bacterial infections, the neutrophils are the ones that show up first. They basically phagocytose the bacteria. Flashback to AMP1 again. The phagosome comes in, the lysosome that has all the digestive enzymes fuses with the phagosome, and hopefully those digestive enzymes are able to kill, basically digest the bacteria. That's what these guys do. So they produce a lot of the chemicals. The granules, basically. See, this one's kind of mad. He looks happy. But now you can start to see some of those purple granules. This one's kind of, he's probably been responding to a bacterial infection. And so you can actually see, when you look at somebody's blood, if their neutrophil count gets to 95, 98%, and all of them look kind of PO'd, chances are this person's having a bacterial infection. Now, the monocytes also, remember I said that the neutrophils and the monocytes were our phagocytic cells. That's their job. They're professional phagocytes. The monocytes are a little bit slower. Sometimes the neutrophils get so excited that they actually overeat and kill themselves. They actually die trying to defend you. And so, when you get an infection, you got the pus and stuff, that's dead bacteria and dead neutrophils and fluid out of your bloodstream and all that kind of stuff. That's what pus process. The monocytes go in and go, oh my God, look at this mess. The monocytes, they're the biggest white blood cells. They can actually eat the dying neutrophils. They kind of come in and clean the mess up that the neutrophils have made. The idea is we send the neutrophils in really quickly, and they keep the infection localized, and then the monocytes come in and help start the healing process, clean up the mess. Make sense? Okay, now, eosinophils and basophils work a little differently. Eosinophils can perform phagocytosis, but that's not their main job. Eosinophils produce something called histamine ACE, an enzyme that breaks down histamine. Now, what do you know about histamine? We've probably all taken an antihistamine, right? If you have sinus allergies, histamine gets released. The histamine comes from the basophils. Basophils are the cells that make you have that allergic reaction. The eosinophils are trying to calm the basophils down. And those of us that have allergies, what happens is our basophils are paranoid. Oh my God, it's pollen, kill it. Overactive. They're overactive. They're hyperactive. You got it, exactly.
They release histamine.
Yes, they release histamine and a bunch of other chemicals. Histamine is one of the big inflammatory. They promote inflammation and inflammatory response. Yeah, exactly. And so the eosinophils, one of their jobs is to release histamine ACE to try to limit the inflammatory process. Don't let it get out of control. Another thing, one of the cool things that eosinophils do is that they're good at defending us against parasitic infections, worm infections or amoeba infections. Worms are multicellular. Even the little filaria, the little baby worms that you can get, those are multicellular organisms. We don't have a white blood cell that's big enough to eat a whole worm. Never mind the 25-foot tapeworm you can get, right? So what happens is if you have a worm, honey's ring. Eosinophils can stick to the outside of that worm, and they can actually release chemicals that begin to kill the worm. So they can't eat the worm, and the worm begins to disintegrate, and the monocyte goes, oh look, lunch. So a lot of times if you think, your child's got worms, they'll look at the blood count, and if the eosinophil count is high, they think, oh, it's probably got a parasitic infection. Okay, again, basophils are basically, they are inflammatory promoters. They promote inflammation. Any kind of cell damage or infection, that basophils are stimulated, and they begin to release histamine, heparin, serotonin, all these chemicals that basically make your blood vessels dilate. Think about a paper cut. You get a paper cut, it didn't even bleed, right? But you did cut some cells. Remember that the bottom layers of your epidermis are alive. They're just not vascularized, right? So you damage some live cells. And then about 20, 30 minutes, that thing kind of swells up, and now that stupid cut gets caught on everything. Gets red and painful. That's inflammation. What's happening is the chemicals that are being released by basophils, they make the blood vessels leaky. So plasma leaks capillaries into the tissue that causes the swelling. That's why it kind of starts to poke up and now catch on everything. It's like when you bite the inside of your jaw, you bite it again because it's swollen. Okay. Lymphocytes. There are actually 3 broad categories of lymphocytes. Lymphocytes can be B cells, or B lymphocytes. They can be T cells, or they can be NK cells, natural killer cells. Now, the natural killer cells, this is the only type of lymphocyte that is not specific. Natural killer cells are kind of like these other types of white blood cells. They're looking for anything that ain't supposed to be there. They're not phagocytic. They don't ingest stuff. What they do is they release chemicals that basically kill cells that don't look right. So the natural killer cells are non-specific. But the other two, the B cells and the T cells, that's your adaptive immune system. B cells, their job, when they are stimulated by some foreign molecule, some antigen, some virus, bacteria, whatever, their job is to, some of these B cells become what are called plasma cells. They develop into plasma cells. And it's actually the plasma cell that produces the antibodies. So if you have antibodies against hepatitis B, that means that you have plasma cells making those antibodies. Every time you get a flu vaccine, you're stimulating a different B cell that matures and divides to form a bunch of plasma cells. Those plasma cells make anti-influenza antibodies. The T cells, well, T cells do two things. T cells can help B cells in fact, they're called helper T cells. Or T cells can actually attack abnormal cells in your body. When they transplant organs, if they can't get a perfect match, they have to give the recipient immunosuppressants. Because if they don't do that, some of their T cells will attack that donated organ, that transplanted organ, because those cells are different than the recipient cells. There are molecules on those cells that are different. They're like, well, that's not supposed to be there. Sometimes, if the organ brings in its own T cells, the T cells in that organ will attack the recipient. You get graft versus host disease. If you've got a cell in your body, and you've got a bacteria sitting out here, or you've got a virus out here, if the bacteria or the virus is outside of the cell, that can be handled with antibodies.
That produce red B cells.
That produce B cells that become plasma cells. Right. If, however, you don't have any antibodies already out there, you've not been vaccinated against these organisms, and this bacteria or this virus gets inside, that's mutated, sorry. If these organisms get inside of a cell, the antibodies can't get to them. Antibodies are big proteins, so they can't get, once they're released into your body fluids, your plasma and your tissue fluid, and you have antibodies lining your mucous membranes, then the only thing that can happen is a T cell can recognize this cell is infected, and what it does is it kills the whole cell. Just some white blood cell leukocyte terms. Remember how many red blood cells we have per microliter of blood? About 5 million. RBCs per microliter of blood. You only have about 6,000 to 10,000. So let's just make, let's say 7 here. That many. So when you look at blood smear, you're mostly seeing red blood cells. Because you got a whole bunch more red cells than you do white blood cells. Make sense? Now, leukopenia would be a low white blood count. Leukocytosis would be a high white blood cell count. Leukemia is a cancer of the white blood cells. Sometimes leukemia starts out, the person is leukopenic because the cancer cells in the bone marrow have inhibited the bone marrow from making normal white blood cells, so their white blood cell count will drop. But as that leukemia gets worse and worse, then they become leukocytotic because the white blood cell count goes crazy, but they're all cancer cells. Of course, leukopoiesis, just like erythropoiesis is production of red cells, leukopoiesis is production of any of the white blood cells, lymphopoiesis specifically the lymphocytes. All right, so we've talked about red blood cells, we've talked about white blood cells, last but not least, our good old platelets. Remember that a platelet is not really a cell. A platelet is just a little bleb of cell membrane and cytoplasm off of a large cell called a megakaryocyte. Megakaryocytes stay in the bone marrow. If you get a megakaryocyte out of your bloodstream, you've got a really bad leukemia. It's not good. Megakaryocytes stay in the bone marrow, and what they do is they just basically pinch off little pieces of themselves, and those little pieces are the platelets. And then those are released into the bloodstream. Platelets, you have somewhere around, let's say, 300,000 of those floating around at any one time. So again, when you look at a blood smear, you see lots of red cells, you'll see little platelets in between the red cells, and every once in a while you'll run across a white blood cell. Now, platelets inside the body live about, not quite 2 weeks, a week and a half, maybe 2 weeks. If you take platelets out, like when somebody donates a unit of blood, they can take the platelets out of that unit of blood, and they're good for about 5 days. They have to put them on what's called a platelet rotator. They have to gently rotate them so they don't stick together. If they start to stick together, they're going to form a clump. So you have to kind of keep them moving, but they only live for about 5 days outside the body. Of course, the big job of a platelet is to start the clotting process. When you cut your finger, when you do a finger stick, first thing that happens is you have a whole bunch of platelets that run and try to patch that hole. And then that forms that little platelet plug, forms the perfect environment to form that fibrin clot, that blood clot on top of it. So that's what we're going to talk about next, is how that works.